Okay, well, thank you very much for sticking it out. We're now in the 5 p.m. session. So this session is, again, exoplanets and habitability, and I will be the chairperson for this session. My name is Victoria Meadows. I'm from the University of Washington and the NASA Astrobiology Institute. And today I'm going to start off with just a 10 to 15-minute overview on planetary habitability, what the big questions are, and something a little bit about the diversity of planetary habitability. And then I will step sideways and turn into somebody else, because I am also going to be given the invited talk for Sara Seager, who is unfortunately unable to be here at this time, and I'll talk a little bit about that later. But first of all, I'll start with the introduction of planetary habitability and just give you an overview of where we think the important questions are and which fields we concentrate on, and also basically a map to the posters as well that are in this session, which are very, very vital. We don't have very many talks, but we have a lot of posters. I'm going to give you a little bit of context for those posters and advertise where we'd like to see those. Okay, so the two big questions in habitability study at the moment are basically what makes a planet habitable? And the second one is, okay, if we learn all the different characteristics and factors that make a planet habitable, how would we go about actually recognizing those characteristics on an extrasolar planet? Because obviously our ultimate goal is to be able to find planets around other stars and to assess their levels of habitability via measurement. So in any talk on habitability, we of course mentioned the classical habitable zone, the Casting-Whitmire-Reynolds 1993 habitable zone. And as you can see, it's basically a diagram that takes the mass of a star, or the spectral type of a star, on one axis over here, and then places a planet at a certain distance from that particular type of star. And in this golden path here, we have the classic habitable zone. But you can think of it more as a surface liquid water habitable zone, because at least from the astronomical perspective, that's what we care about most. Because we want to build large telescopes to be able to, again, assess that habitability, to measure it. And to do that, we very much want the biosphere to be on the surface of the planet and not hiding under layers of rock or ice. So we really do concentrate on the surface liquid water habitable zone. However, as we are learning, as we go into this field, it's really not quite that simple when it comes to assessing habitability. And this diagram is intended to be scary. And what it is showing you is that if we go with this sort of mantra of, yes, we want a planet that has liquid water on its surface, there's actually a large number of factors that go into determining planetary habitability. And these can be grouped into three basic areas. One are the stellar effects, the effects of the star on the planet. The others are the planetary system effects, the effects of the sibling planets on the planet that we care about, the one that is potentially habitable. And we heard that wonderful talk from Alessandro Morbidelli yesterday about how, if the Jovian planets aren't happy, nobody's happy. So it very much, the planetary system you find your potential habitable planet embedded in will say something a lot about the habitability of that planet. And then, of course, you have the actual planetary properties of the planet. And many of those will not just be, whether or not there's enough insulation hitting this planet, but also things like, is it protected from ultraviolet radiation? Is it dynamically stable? Does it have dynamical characteristics that would lead to long-term climate stability? So we certainly do have a quite complicated picture of planetary habitability if we sit down and think of all the different things that can affect it. And I often hear the criticism that concentrating on liquid surface water is maybe too restrictive for a vision of the habitable zone for extrasolar planets. But I would argue that with even that one single criterion and all these factors that affect it, there are multiple paths to a liquid surface water planet. You can imagine a very different planet with very different atmosphere, mass, parent star. It would still be a habitable planet, but it would look nothing like the Earth. Okay, so I think if I try and summarize where I think the major research areas in habitability are nowadays, we have basically four major areas. One is this idea of exploring the limits of habitability, looking at all these different types of factors. So looking at the influence of stellar, planetary system, and planetary properties on planetary habitability. And there's kind of a flip side to that, which is where our biological colleagues come in, and they help us with field work and laboratory work that actually looks at the limits of life itself. So a better understanding of what planetary conditions could potentially support life if we push life to its limits. The other type of study that we do in planetary habitability, which has only recently become possible, is we now know enough about particular planetary systems that we can have people go in and assess habitability for a given planetary system. And so later on in this session, there'll be a talk about from Robin Wordsworth, and Frank Celsus does this sort of work as well, where they go into a particular system and try and understand the different factors that affect habitability of planets that have already been found in that system. The third one, which is one I'm particularly interested in, is this question of detecting habitability. Okay, let's say we start to understand what factors affect habitability. Now, what sort of things can we measure? What is going to be achievable with spacecraft or ground-based facilities that are currently planned or in development? And really just trying to get down to the nuts and bolts of, okay, how do we prove a planet is habitable based on measurements? And then finally, and this is not so much an introducing this concept, but really a revision and summary of what you've heard from multiple talks so far in this session, which is that the habitability of planets around M dwarfs is very much a hot topic at the moment in this particular field. And that is partly driven, actually largely driven by the fact that these are likely to be the first planets that are discovered which are potentially characterizable for habitability. So if I go into our poster session now and our talks as well, and we go back to this scary diagram of all the different factors that lead into potentially having liquid water on the surface of a planet, you can see in our session we have many different posters that address aspects of this, from questions of stellar metallicity and the formation of terrestrial planets, which is the starting point. So planet formation is part of what feeds into this as well. We will have a talk later on by Antigona Segura on the effect of stellar flares on planetary habitability. There's a very nice poster by Sean Dumble-Goldman on the effect of hazes and water world planets on the potential limits of habitability. This is a case where a haze, for example, might help to cool a planet and allow it to move further in towards its parent star. There's a study by Grenfell et al. On the photochemistry of specific systems, looking at habitability. And also a nice poster by Wordsworth looking at evaporating hydrogen atmospheres and different periods in which they might, in fact, become habitable. And then up over here on the dynamics side, we're going to get a talk from Renee Heller on the effects of tidal interaction on a planet. And by that, what we're talking about is the interaction between the planet and the parent star, but not in the classical radiative sense of sunlight hitting on the planet, but the gravitational effect of the star on the planet. Turns out we're now understanding that that's becoming very, very important for assessing habitability as well. So Renee will talk about that. You've already heard the talk from Mercedes about magnetic fields and how that might eventually feed into habitability and how it might be not quite so dire for M-star planets as far as maybe not having strong magnetic fields. And then finally, of course, we heard a provocative talk earlier today about even breaking out of the liquid water requirement for life as we know it and considering alternative biologies and alternative chemistries and solvents for life. Okay, so that's kind of where that all fits into that diagram. The other things we have in this session, and there are many, many posters on this, is from our biology colleagues looking at, again, the limits of life. And so we have several studies that are looking at things like the effect of cosmic rays on microorganisms, looking at desiccation and the survival of life in extreme water-poor environments on the Earth. A poster on looking for life in high-temperature worlds, pushing the limits of life to the high-temperature area. And this is actually not in our poster session, but it is relevant to what we are doing. And that is a poster by Steve Milkey, looking at measuring the efficiency of different chlorophyll pigments as we push to longer and longer wavelengths. And this becomes more relevant when we're talking about potentially photosynthesis on either haze-covered planets or planets that are orbiting around M dwarfs. So that was kind of an overview of the limits of habitability, things that factor into it, and the limits of life. So this other aspect of detecting planetary habitability. There are many ways we can try to do this. Of course, all theoretical at the moment. We don't yet have targets we can do this on. But there's a lot of theoretical work at the moment looking at, and also work that uses actual data from the Earth to try and determine how detectable it would be to actually see surface liquid water directly, for example. So there's a phenomenon called glint, where light reflects off an ocean, and in the glint case, it may be possible to see that even in the disk-averaged Earth. I should have made this point that when we're trying to detect habitability, we don't have a lovely image of a planet sitting there in our telescope, we just only have this pale blue dot. So all of these techniques are to try and get information out of that pale blue dot on whether or not the planet is habitable. So we could try to directly detect surface liquid water. We used to think that was impossible. We think it might actually be something that is achievable now. We try to directly detect the surface temperature and pressure, if that's at all possible. But what will most likely happen for most planets is that we'll have to characterize the environment as best we can, and in that sense try and understand what the surface and the atmosphere is like, to take a census of greenhouse gases, and to, again, understand the planetary system environment it's bedded in, the other planets, and characteristics of the planets itself, to put together a self-consistent picture that limits the sort of range of habitable environments that a particular planet could have. So in those areas, we have a bunch of posters as well, which I encourage you to go look at. We have a paper by Robinson et al. On whether or not we can detect a moon around an Earth-like planet and the techniques we might use to do that, both photometrically and spectrally. We have a paper by me on trying to detect the temperature of a planet in disk-averaged mid-infrared radiation, the types of errors you might encounter in doing that. We also have two papers, one in this session and one in the P8 session, that look at light curves for the Earth through time to see whether we could determine from the light curves alone if the Earth was habitable at previous eons, like the Archean. A lovely paper by Luc Arnauld on using Earthshine, so light reflected off the moon, that is sort of a proxy for the disk-integrated Earth data, and studying both photometry and spectra from doing those observations. And a paper by Antigona Segura, different from her talk, on the habitability of the specific system Gliese 581d. Okay, so just in the sort of pie in the sky area, these are the missions we hope to have to do planetary characterization. I'm not sure I will ever live to see these launch. These are all, as Frank said, they are beyond the horizon for these spaceflight organizations like NASA and ESA. The actual correct term is beyond the budget horizon for these missions. And so we still have them in concept within the Decadal Survey. We have money to start working on technology for some of these, but these are certainly a long way off. Okay, and Sara did want to make this particular point, because this is part of her expertise, is looking at transits for planets. And again, for the M-dwarf argument, she really wants to hammer home that it's not just the probability of being able to see the planet around the M-dwarf. There's sort of three factors that make discovering small planets around M-dwarfs particularly attractive. One is the probability that you will actually see it, and this has to do with the range of angles between the star, its planet, and you, where you could be looking at this system and still have the planet appear to transit the star. If the planet is very close to its parent star, that range of angles is much larger than if the planet is much further away. And so for M-dwarfs, because their planets are close to the parent star, they've already have that advantage. Sorry, for habitability, they're close to the parent star. They already have the advantage that a habitable planet around an M-dwarf is a more detectable planet just based on geometric probability considerations. And that's shown in this diagram here. These are all sort of drawn roughly in the habitable zone to scale for these different stars. The other thing is if it's in the habitable zone of an M-dwarf and it's very close, it has a very short period, which also makes it easier to detect because you see the planet go around and come back multiple times in a relatively short period. And typically, you want at least 2 orbits to confirm that you have something. Again, the transit depth is better because the depth of the transit, how much the starlight dims, is really a ratio between the size of the star and the size of the planet. If the star is small, it's more detectable. So again, there really are very compelling observational reasons for why we want to go around after M-dwarf planets. Okay, so again, M-dwarf habitability. I guess I mentioned this in the previous talk. It does have some issues, but this is sort of an area where we now have to start to think about a very different type of habitable zone. We're used to the habitable zone, the G-star habitable zone that we currently sit in, where we don't have to worry about tidal effects, where we don't have to worry so much about the activity of the star. And so now we have to start thinking about these other aspects and how they impact habitability. So given that we probably will have super-Earths in the M-dwarf habitable zone as our first observational targets for things like transit transmission, it's interesting to think about this because we really don't have an example of a super-Earth planet in our solar system. The largest terrestrial we have is the Earth. So we're now talking about planets that are, say, 10 Earth masses, maybe 2 times the Earth's radius. They probably have very, very different compositions, and we really fully don't understand what they would be like. And we've had a lot of modeling. A lot of it goes in one way or the other, looking at, for example, the internal structure of these sorts of bodies, even their composition based on the star. How plate tectonics operates on these objects, because we think that plate tectonics is important for buffering climate over time. Do they have plate tectonics? Do they not have plate tectonics? Do they have episodic plate tectonics? So there's at the moment a very rich theoretical area where we're trying to explore in sort of different physical and chemical regimes what these planets might be like. We also care about the atmospheric composition and structure and what that might be like. And for us, the classical terrestrial planet is the one we're standing on as far as a habitable planet's concerned. But if you think about these extrasolar super-Earths, they may have very different chemical compositions in their atmospheres. And I've taken these 3 examples from a review that was done by Deming and Seager, of which there were 5 examples of different types of super-Earth atmospheres. The first couple being, I think, something with no atmosphere. And the 3 that I have up here are planets where we have an outgassed hydrogen-rich atmosphere that's actually retained against atmospheric escape. And so you end up with a terrestrial planet with a fairly reducing type of atmosphere. You can have another one where you do have your outgassed atmosphere, but in this case the hydrogen is lost. And so you can end up with something that's a bit like the Earth's earliest atmosphere. And then the example of sort of young, cold, or more massive super-Earths, where they have the primordial hydrogen-helium-dominated type of atmosphere, so more like a Jovian type atmosphere overall. But again, these are not classically what we would think of in the solar system as a terrestrial-type planet. Sara also wanted me to mention this particular paper, and this is going towards sort of rethinking the habitable zone and also looking at the habitable zone in the context of the type of atmospheres we might see for super-Earth planets. So if we had a super-Earth atmosphere with a particularly hydrogen-rich atmosphere, and this is a study where I think it was with pure hydrogen atmosphere, so there's maybe some issue with having other constituents in the atmosphere. But this is work by Pierre Humbert and Gaidos, where they actually looked at collision-induced absorption from H2 in the atmosphere as a potential incondensable greenhouse gas for these planets. We're not used to thinking of hydrogen as a greenhouse gas. Normally it's on a Jovian, and it's not something we think about as far as greenhouse is concerned. But with these models, they were at least able to make the first steps towards considering a sort of habitable greenhouse gas atmosphere that is hydrogen-dominated. And what they showed was that they could greatly extend the habitable zone out to about 1.5 AU for an M-dwarf, which is typically the habitable zone around an M-dwarf is between 0.1 and 0.2 AU. So we're pushing out to 1.5 and out to 10 AU for an Earth-like planet. So, I mean, this is, again, a preliminary foray into it. And in fact, I think there's a paper also by Robin Wordsworth actually looking at what happens when these sorts of atmospheres start to evaporate and where you might, in fact, find the sort of sweet spot in the right amount of hydrogen for a certain period of time on that particular planet. So go see Robin's poster as well. So I will now talk about biosignatures to finish up here. And so Sara wanted to use this slide just to point out that, when we're talking about diversity in exoplanets, she's very much inspired by the diversity of life that you find on Earth and the way that life is so tenacious and is able to survive in many different environments. So we're going to talk about biosignatures. I'll just give you a very quick overview of what that is. And so in our case, the definition, I don't know if it's approved or whatever, but what we use in extrasolar planets, the definition of a biosignature, it's a sign of life. In our case, it's an astronomical biosignature, meaning it has to be detected remotely or via astronomical instrumentation. And it has to be a global scale, photometric, spectral, or temporal change in the planet's environment that is indicative of life. And it has to be global because, again, we're looking at that pale blue dot. We really want something that's not in some special niche on the planet, but in fact covers the entire planet. And photosynthesis is a particularly nice metabolism for that because it really does cover the entire planet. So if we look at the Earth, it shows us that we can have biosignatures in 3 main flavors. One is changes in the planet's atmosphere due to the effect of life. 2, changes in a planet's surface, either reflectivity or surface coverage overall, that is indicative of life. And also changes in a planet's appearance over time. And the change in the planet's appearance could either be in the abundance of a gas or in the reflectivity that you see on the planetary surface. So just briefly, sort of the atmospheric biosignatures we typically think about are things like oxygen and ozone, especially when they're in the presence of methane, and I'll get into why that's important. And over here, the sort of surface signatures we see are massive changes in the reflectivity of plants, longwood of 0.7 microns. This is a phenomenon called the red edge. And it's kind of analogous for the astronomers here to the Lyman alpha break, in the sense that it's a very sharp transition in the spectrum. We're not exactly sure exactly when it's going to be wavelength-wise, but we would certainly look for that type of behavior, which is due to sort of absorption from chlorophyll initially here, and then a very rapid change in reflectivity as the plant attempts to get rid of radiation it doesn't want at longer wavelengths. But I really want to stress in this talk, really, that if you're trying to say that something is a biosignature, it has to be identified in the context of the environment that you find it in. There are examples where things that we might think of as biosignatures, like oxygen, for example, yes, that could be the sign of photosynthetic life, but it also could be due to a buildup of, say, a photolysed gas on a planet where we don't have mechanisms for getting rid of that. So it really is very important to not just say, you know, that's a definitive biosignature, but to try and characterize the environment we find it in to see whether it is, in fact, an odd phenomenon that could only be explained by life. And then, of course, there's this concept of anti-biosignatures, which I think was maybe first brought up by Dave Desmarais in a workshop we had. And that is when you see things that you think, gosh, you know, life would have evolved to use that. Why is it still around? And my colleague Yuk Young likes to make the analogy that if you were to walk into a town in France, for example, and you found euro notes blowing through the street, like 20 euro notes blowing through the street, you'd probably realize that there was nobody living there. Okay, so that's an example of an anti-biosignature. Yeah. And that's just an example of a temporal biosignature, which I didn't go into. And this is the classic rug plot for carbon dioxide. It shows seasonal variations in carbon dioxide that are due to the cycle of vegetation photosynthesis on our planet. Okay, so how do we generate an atmospheric biosignature? This will become relevant shortly. There are sort of 3 main ways, and what I'm talking about here is trying to go through the intellectual steps to try and figure out, okay, which gases are going to end up being biosignatures in a planetary atmosphere. So there's 3 things that they have to do. They have to have a biological source, so, I mean, your gas has to be produced by life, whether either directly as a product of metabolism or some kind of breakdown product. It has to survive in the atmosphere long enough to build up to detectable quantities. And ultimately, it has to have spectral features, preferably in the wavelength range your telescope happens to operate in. Okay? And so, for example, nitrogen fulfills the first 2 requirements in our atmosphere, but it's dreadful at spectral features. It has very few. So nitrogen is a stealth gas. It has some features in the UV. It has sort of 1 absorption in the near infrared, but it's pretty much non-existent in the rest of the spectrum. So those 3 things do have to be fulfilled so that you actually have a biosignature. And sorry, what this plot is showing here is the sources coming off the planet. And here we're showing the fluxes of gases coming off the Earth, this huge diversity of fluxes. And then Tim Lenton, who did this plot, just basically took away all of the biological fluxes and left us with only the planetary geological fluxes, and this is what you would see coming off the planet. And so it's very clear that life is a huge producer of surface gases from the planet. She said it's long. Yeah.